Hi everybody, just wanted to make a little video here on some analysis proofs and just to kind of give you some tips and tricks of common things to try in order to achieve your goals here. Um, so basically the thing is we're needing to make analysis well, inequality arguments, I think, and we're not as familiar with that as we are with equalities usually. But anyway, here's the definition. So if we have A as a limit point of the domain of F, which is just a fancy way of saying that there's lots and lots of points close to A in the domain of F. Anyway, we say the limit as x goes to A of f of x is equal to L, if and only if for each epsilon greater than 0 there exists a delta greater than 0, such that whenever 0 is less than the epsilon value of x minus a is less than delta, that implies that the epsilon value of f of x minus L is less than epsilon. So put differently, this says that whenever you're within delta units of the limit point, but not necessarily at the limit point, then the values of the function are within epsilon units of the limiting value L. All right. So I have some pictures in my notes that kind of give you a more direct visual representation of that. We'll probably talk more about that one in the next class, maybe. Anyway, so let's look at a specific example where we have to prove something using that definition. So here I have f of x is 2x squared plus 3x plus 4, and I want to show that the limit as x goes to 2 of f of x is equal to 18. All right. Of course, you probably derived this back in calculus using limit laws and such, but now I want to show you how to prove it using an epsilon delta proof. So our goal is to show that the epsilon value of f of x minus L is less than epsilon, given this condition over here. All right. So what that means is we need to find delta as some function of epsilon. That may require some tricks, but here we go. So we're going to look at f of x minus L is equal to that, which simplifies to this. And I know, before I even get to the next step, that because I'm looking at a limit at 2, there's going to be an x minus 2 that factors out of this. It's just how it goes. So indeed, this factors to x minus 2 times 2x plus 7. All right. Now, the good news is that then by properties of epsilon value, right, like the epsilon value of a product is a product of the epsilon values. So we get an x minus 2 epsilon value, we get epsilon value 2x plus 3. Now, x minus 2, we have control over that in the structure of the proof. We're assuming that the epsilon value of x minus 2 is less than delta, so we can replace that with a delta over here, right? But then we're stuck with this pesky 2x plus 7 epsilon value, and that's going to be large, right? So how do we deal with that? So if you think about it, it's about 11 for x approximately 2, right? So it's not small. We have to do something to deal with that. Let me show you how. So this is kind of a standard trick. If we also could build that our delta, and we choose the delta, all right, we choose the delta, we can choose it to be less than or equal to 1. And if we do that, that puts us within 1 unit of our limit point, right? Which means essentially that, minus 1 is less than, so notice that if this absolute value of x minus 2 is less than 1, that means that minus 1 is less than x minus 2 is less than 1, right? And then you can do some, inequality steps here to get from this to that, which gives us that, ultimately 2x plus 7 is actually between 9 and 13. You can kind of look at it graphically like that, right? If we have inputs, right? If we have inputs that are down here, right? Then that puts outputs that go between 9 and 13, and man, these markers are dead. Anyway, as such, notice that here's another trick. So 13 is at a bound above. Minus 13 is below is below 9, of course. So that allows us to trade. If you have something, the negative something is below and the positive something is above, that gives you license to write the absolute value of that something is less than that above and below bound, right? So in this case 13. All right. Now this business down here is somewhat irrelevant. I'm just showing you what the graph of the function we're looking at, looks like. I didn't actually use any of this. I was just messing around. So you can ignore it. All right, so that's all scratch work. That brings us to the actual proof. All right, almost. So next up here, just a few concluding thoughts of my scratch work. So we found if delta is less than or equal to 1, we could make the absolute value of 2x plus 7 less than 13. So if I have 0 less than x minus 2 is less than delta, that implies that f of x minus L absolute value is less than delta times 2x, absolute value 2x plus 7, which is equal to 13 delta. I guess I could say less than or equal to. Less than or equal to. But, alright, so here we go. Finally the proof. Right. Notice, and I keep emphasizing this, that just because I did something in the scratch work doesn't mean I can omit it in the proof. The proof must be self-contained. Here we go. Let epsilon be greater than 0. All right. Choose delta equal to the minimum of 1 in epsilon over 13. If that's the case, that means that 1 is less than or equal, delta is less than or equal to 1, and delta is less than or equal to epsilon over 13. We get both at the same time. That's the beauty of the minimum. Oh, man. The wind is upon us. Just a second. All right. So, if x is a real number and we have that, then, of course, the difference between x and 2 is at most 1. Right, the absolute value of x minus 2 is at most 1. Hence, we have minus 1 less than that, which implies this, which implies that, which implies... I'm just retracing the steps in the past page, right? But again, they should be here. I shouldn't have to look outside the proof to understand the proof. All right? That, which implies this, which... Okay, so we got 2x plus 7 absolute value is less than 13. Consider, for f of x equals to this and L equals to 18, we have that the absolute value of f of x minus L is equal to this minus this, which is, 2x squared plus 3x minus 14, which factors, which by the property of absolute value is the absolute value of the product, which then, by our construction, right, is less than delta times 13, which is less than or equal to epsilon over 13 times 13, which is epsilon. Thus, the limit of 2x squared plus 3x plus 4 is equal to 18 by the definition of the limit. All right. Remark. Well, you need to know that the absolute value of the product is the product of the absolute values, and also this is a really important idea that absolute value being less than delta is interchangeable with minus delta less than a less than delta, right? For positive delta, of course. And we'll see that there's a few other tricks in the future examples, but those right there are obviously big ones. All right, so next up, this is a slightly more troublesome example. I think this one's more troublesome than the ones I gave you in your homework. All right. But I figure it's good to see a harder example. All right. Sorry, Al. The paper's getting out of order over here. So come back. So we have the square root of 2x plus 1. Square root of 2x plus 1, and I'm going to study the limit as x goes to 4. I'm going to show it's equal to 3. All right, so this is what I'm after. I want to find, this is what I want to happen, right? This is scratch work, all right? So I thought about it. I'm like, oh, well, okay, well, x minus 4 is actually 1/2 of 2x minus 8, which is actually 1/2 of 2x plus 1 minus 9, which is actually like that. So I can factor this into that, all right? In other words, and maybe you would think of it this way, you could rationalize this, rationalize the numerator by unrationalizing the denominator. It's kind of like undoing rationalization. But anyway, it's multiplication by 1. And when you do that, we get this, right? But then, if you look at that, of course, the x minus 4 we can make less than delta, but the 2x plus 1, if we think about it, if we do that delta, down here, if we're within 1 unit of 4, then through this chain of logic, we can get that the square root of 2x plus 1 plus 3 is actually bigger than 3 plus root 7, which means that if I replace So this is larger than that. I've replaced the denominator with a smaller quantity, thus making the fraction larger. That's another important idea. So the rules for inequalities with the denominators and the rules for inequalities with numerators kind of inverse, right? So that's less than or equal to, if I want that to be less than or equal to epsilon, that suggests I should make a delta equal to epsilon times 3 plus root 7 over 2. All right, so now we're ready for the proof. Let's do it. Let epsilon be greater than 0, and choose delta equal to the minimum of 3 plus root 7 over 2, and 1. Delta is less than or equal to 1, and delta is less than or equal to 3 plus root 7 epsilon over 2. So, if x is a real number, and 0 is less than epsilon value x minus 4 less than delta, then the epsilon value of x minus 4, of course, is less than 1, which implies this, which implies that, which then, multiplying by 2 gives me 6 less than 2x less than 10, and so 7 is less than 2x plus 1. Remember that the square root's an increasing function, so the square root of 7 is less than or equal to the square root of 2x plus 1, which says that 3 plus root 7 is less than or equal to, square root of 2x plus 1 plus 3. Great. Now consider that the absolute value of 2x plus 1, square root of 2x plus 1 minus 3, is equal to, well, multiplying above and below by that non-zero quantity gives me this. Just multiplying by 1. Do the algebra. This squared, the cross terms cancel, so we have minus 9. Squaring that, we get to 2x plus 1 minus 9 over the square root at the bottom. And then, of course, that we pull a factor of 2 out. That gives us 2 times the absolute value of x minus 4. And downstairs we have the absolute value of 2x plus square root of 2x plus 1 plus 3. But we have previously argued that that is this is larger than 3 plus root 7, which means that I'm decreasing the size of the denominator, thus making the fraction larger. And upstairs, I'm replacing x minus 4 with a delta, which is larger, so this fraction is larger than that one. This is a legit inequality. And as such, we have, I got 2 over 3 plus root 7, and then my delta, remember delta is less than or equal to, by construction, 3 plus root 7 over 2. And hence I get epsilon. So this is the neat trick. Using the minimum function, we can get two things at once for the delta and put those together in concert to achieve the desired inequality. Thus, the square root of 2x plus 1 as x goes to 4 is equal to 3 by the definition of the limit. All right. Whew. So that one was a little bit tricky. We need some algebra there that wasn't immediately transparent. So next, this example 3. See if I can find my papers here. Oh man, hold on a second. I think I might be missing a page. Where's my other page? I got page 4 and I got page 6. Where's my page 5? Oh man. Is it right under here? Well, duh. Smart. Anyway, so here we go. This one's similar to one of your homework problems, if you're in Math 200 of, Spring 25. Oh, a blue jay. Cool. Anyway, so I want to show this limit. All right, this is going to take us a little bit of trouble. We're going to get it though. So we take the difference of the limiting function and the limiting value, like that, make a common denominator, all right? And I don't like working with a to the 4th minus x to the 4th, so I'm just flipping it to x to the 4th minus a to the 4th. I can do that because remember that the absolute value of minus a is equal to the absolute value of a for like any a, right? So if I take, I can cancel the 16s and pull the minus. You basically flip the minus. So that's a legitimate step right there. Now downstairs, of course, I still have that. But this upstairs factors to x minus a, x plus a, x squared plus a squared, right? Now this is scratch work, so if I skip a step, it's not a big deal, all right? although it's a slightly bigger deal because I'm trying to teach you guys, so I'm trying not to skip any steps here. But anyway, um, so this is x plus a. So if you look at this, what we need then is we need to get our pause on x plus a absolute value, x squared plus a squared absolute value. Of course, this is positive, so we don't really need the absolute values. And yeah, so like a to the fourth plus 16 downstairs. Well, that is what it is, and it's positive. And then, of course, the absolute value of x to the fourth plus 16, which is, again, I could drop the absolute values because it's clear that x to the fourth plus 16 is positive as well. So anyway, if we could find a bound on all of that, let's say m, then basically we would have this less than that, and if we could make the if we could make delta less than or equal to epsilon over m, then we're golden, you know. So if we make our delta less than or equal to 1 and sort through things here. Now, the difficulty in this problem that wasn't present in the previous one is that the limit point's arbitrary, right? So we've got to deal with a being a variable. But that's not an insurmountable problem. And you don't even need to break up into cases if you are careful in your methods. So check this out. We have absolute value of x minus a less than 1. So we can unwrap that to this compound inequality, which then adding a, right? Whether a is positive or negative, we can add it across the inequality. That's fine. Then that gets us this, which then, if we add a again, gets us this, right? So now I've got my pause. I've got x plus a in my sights. Now, in order, I want a statement about the absolute value of x plus a, right? So the next step, and this is kind of a trick, so watch it, is that 1 plus 2a is less than or equal to its absolute value, and 2a minus 1 is greater than or equal to minus its absolute value. All right? And then if you think about it, whichever one of these guys is bigger, we know that x plus a is within the larger of these two values, distance from the origin, which is to say that the absolute value of x plus a is less than the maximum of the absolute value of 1 plus 2a and 2a minus 1. So that's kind of nice. We don't need to break into cases. We can use this kind of argumentation. All right. And likewise, skipping back a step or two, a minus 1 less than x less than 1 plus a yields that the absolute value of x is between the maximum of 1 plus a and a minus 1. All right. And I'll call that m2. So absolute value of x squared is less than m2 squared, and then adding a squared. Notice that the absolute value of x squared is x squared, right? Fun fact. So then that gives me this. So I've got 1, I've got 2, and so it remains to tame 1 over x to the fourth plus 16, but then I was like, oh, duh. So of course, 1 over x to the fourth plus 16 is, it's less than 1/16, okay? Less than or equal to 1/16. It's only 1/16 when x is equal to 0. Otherwise, it's smaller than 1/16. All right, so I think the comment at the bottom of the page here isn't quite right. Let's go ahead to the proof. When I actually wrote out the proof, I realized that I was a little bit too naive in my scratch work. Sometimes that happens, because I think I was forgetting about the a to the fourth plus 16. So continuing here. Continuing. We have, let epsilon be greater than 0. Suppose a is a real number. I'm going to let L be the maximum of 1 plus 2a and 2a minus 1. And I'm going to notice that L is not equal to 0, right? If one of these is 0, the other one's not, and vice versa. I'm going to let little m be the maximum of 1 plus a and a minus 1. Again, notice that if this is 0, that's not 0, and vice versa, right? This is 0 if a equals to 1. If a is equal to 1, this is 2. This is 0 if a is equal to minus 1. If this is, but if a is equal to minus 1, this is minus 2. So, you can't have both of these be 0, all right? So my L is not equal to 0, my M is not equal to 0. That's important to notice, because I'm going to construct delta as the minimum of 1, and the quantity, maybe hard to read here, my apologies, 16 epsilon times quantity a to the fourth plus 16 divided by L times parentheses m squared plus a squared close parentheses. This is a reasonable quantity to construct because it is positive. It is a legitimate choice of delta. All right, so pick a real number. let it be, within delta units of A, then that's within 1 unit of A by our construction, since delta is smaller than or equal to 1. And as such, we can retrace our steps. We have, 1 less than x minus a less than, minus 1 less than x minus a less than 1, which implies that 2a minus 1 is less than x plus a is less than 1 plus 2a. And that implies that the minus the absolute value of 2a minus 1 is less than x plus a is less than the absolute value of 1 plus 2a. Thus, by our construction of L, minus L is less than x plus a is less than L, and we find that the absolute value of x plus a is less than L. I'll call that 1. All right. Further, notice that a minus 1 is less than x is less than a plus 1, which implies the absolute value of x is less than the maximum of these two things, but that's m. Therefore, the absolute value of x squared is less than m squared, and thus x squared is less than m squared, which gives us, adding a squared across the inequality, that x squared plus a squared is less than m squared plus a squared. Let's call that 2. Consider then that the difference of 1 over x to the 4th plus 16 minus 1 over a to the 4th plus 16 is equal to this, making a common denominator. And as such, we can factor the denominator. Well, first of all, going from here to here, property of absolute value is that the absolute value of, let's say, I'm trying to think of some other letters, like u over w, right? It's equal to the absolute value of u over the absolute value of w. That's another property of absolute value we can use, and I am. So there we go. Now that factoring is equal to x squared plus a squared times x plus a times x minus a, and I dropped the absolute value downstairs because, of course, x squared plus 16 is positive and a to the 4th plus 16 is positive. And then, well, that is less than or equal to, now I traded my x to the 4th plus 16 simply for 16, as is my right, and because I made the denominator smaller, which makes the fraction larger. And then I have a to the 4th plus 16 still there, and then x squared plus a squared, we don't really need absolute value because it's positive. Then we got absolute value of x plus a, and finally, last but not least, well, actually it is least probably, absolute value of x minus a. All right, so then, lo and behold, that gives us less than this. So I traded my x squared plus a squared for m squared plus a squared, as we had back up in 2. That's using 2. And I'm trading the x plus a for L. That was 1. So using 1 and 2. And I've got my delta. But remember, delta is by construction less than or equal to this jazz over here. And of course, we've constructed that so that it cancels, leaves me an epsilon. Therefore, the limit as x goes to a of 1 over x to the 14th, x to the 4th plus, oh, I'm glad I didn't say 14th, that'd be worse. X to the 4th plus 16 is 1 over a squared plus 16 by definition of limit. So I think in your homework, I may have given you 1 over x squared plus something, x squared plus something reciprocal. The tips and tricks I used in this example can be probably modified fairly easily to solve that homework problem. All right? Just saying. Of course, if you'd like to do it your own way, you're welcome to. All right? Just, do it correctly. All right. So next up, sequential limits. So sequential limits, I had to do some old school editing here on my first page. So let's get this into play here. All right, sequential limits. Eventually I'll get it set up here. All right. So here's the definition of a convergent sequential limit. We say the limit as a sub n, as n goes to infinity, is equal to L, or simply a sub n goes to L as n goes to infinity, if and only if for each epsilon greater than 0, there exists some natural number big N, such that little n greater than or equal to big N implies that the absolute value of a sub n minus L is less than epsilon. All right. Now, so here's a simple example to get us started. Suppose we have a sub n is 1 over 3n plus 1. I want to show that that limits to 0. So I look at the absolute value, which of course simplifies to this, and then, I can make the denominator smaller by not adding 1. This is a smaller quantity, which makes the fraction larger. I want that to be less than epsilon, so that suggests I maybe should use the ceiling function. If I use 1 over the next largest integer to 1 over 3 epsilon, the ceiling function, if you like, then that should do it for us. So let epsilon be greater than 0. Choose n as the next positive integer greater than or equal to 1 over 3 epsilon. Then it's true that if n is the natural number that is larger than or equal to n, then that's larger than or equal to 1 over 3 epsilon. And as such, we get n, little n, is greater than or equal to 1 over 3 epsilon. But that implies that 1 over 3n is less than or equal to epsilon. And so then, if I look at this absolute value is equal to that, which is strictly less than that, which is less than or equal to epsilon by construction. Therefore, 1 over 3n plus 1 goes to 0 as n goes to infinity by the definition of the sequential limit. So that example was pretty easy. Let's look at one that's a little bit trickier, but not super tricky. I think this one is very comparable to the homework problem I assigned you guys, if you're in my Math 200 class from Spring 25. Anyway, let's see here. Get my cover sheet. So let's look at 3n over 2n plus 7. All right. If I look at, I know that the limit of that's 3 halves as n goes to infinity. So I'm going to look at an minus 3 halves. So I have 3n over 2n plus 7 minus 3 halves, which is this, by making common denominator. Canceling stuff out, I get 21 over 2 times 2n plus 7. If I make the denominator smaller, it makes the fraction larger, so I can trade this out for 4n. So it looks like I've got 21 over 4n. If I could make big N such that 21 over 4n was less than epsilon, we'd be in business. That suggests to me we should choose n as the ceiling of 21 over 4 epsilon. It seems like there's a it looks like we're going to use a ceiling function in these problems. Anyway, that's what I'm doing. So here we go. Let epsilon be greater than 0. Let n be the ceiling of 21 over 4 epsilon. Then if n is greater than or equal to n, that implies that little n is greater than or equal to 21 over 4 epsilon. But for n greater than n, we find that epsilon is greater than 21 over 4n. Consider then that the difference of 3n over 2n plus 7 and 3 halves is equal to the absolute value of this, making a common denominator. But then, doing algebra, that gives me minus 21 over 2 times 2n plus 7. And then, that simplifies simply to 21 over 4n plus 14. Hey, quiet. Which is less than 21 over 4n. I said quiet. 21 over 4n, which then is less than or equal to epsilon by construction. Lo and behold, we have shown that by the definition of the limit, as n goes to infinity, 3n over 2n plus 7 is simply 3 halves. And there you go. All right. Now there's one other kind of limit I asked you to calculate in the homework from the definition, like prove. And that was a divergent limit of a sequence. So here's the definition. Now I have said greater than or equal to here. Some people might say greater than. It doesn't really matter. I'm just going to leave it greater than or equal to. So the limit as n goes to infinity of a sub n is equal to infinity if for any m greater than 0 there exists an n for which n little n larger than or equal to big N implies that a sub n is greater than or equal to m. This is a way of formalizing the concept that the values of the sequence grow without bound as n goes very large. So here's a sample. There's a couple of really easy examples here to start with. If we have a sub n equals to 3n, if we simply let n, big N, be the next integer larger than or equal to m over 3, then we have n greater than or equal to m over 3. And if n is an integer which is larger than big N, then it's larger than big M over 3, and consequently 3n, which is equal to a sub n, is greater than or equal to m. Thus, as 3n goes to infinity, 3n goes to infinity as n goes to infinity, by the definition of the divergent limit of a sequence. Well, I didn't even do scratch work for that one. I just wrote it down. All right. And I think the same is true for the next one. Maybe. Let's find out. Now I've got n squared plus 1. All right. And so here we want n squared plus 1 greater than or equal to m. So that's like saying n squared is greater than or equal to m minus 1. So yeah, I guess I need to look at like square root of m minus 1 as a potential big N. So here's the proof. Let an equal n squared plus 1. Consider m is greater than 0. So I said, okay, I'm going to look at two different cases. The one case is 0 to 1 inclusive, right? In those cases, this is imaginary. But in those cases, it's also true that n squared plus 1 is greater than or equal to 2, which, by the way, is greater than m. So clearly the values of the sequences are larger than our positive bound. All right, so the interesting case, of course, is if m is positive and greater than 1, then I can let n be the ceiling of the square root of m minus 1. And notice that for that ceiling function, we have that n squared is greater than m minus 1, which is to say that n squared plus 1 is greater than or equal to m. Thus, that's what we wanted to show, that the values of the sequence are larger than or equal to our arbitrary m, which is positive. Thus, a sub n equal to n squared plus 1 goes to infinity as n goes to infinity by the definition of the limit. You might say by the definition of the divergent limit, if you like. But I do think about the limit as a coherent whole, a concept which extends past just one particular subcase of it. Anyway, this one is kind of dual to your homework problem. I think I asked you guys about like the natural log. Here's a proof of a exponential. They're kind of the same. So I want to show that the limit as n goes to infinity of e to the 3n plus 2 as n goes to infinity is infinity. All right. Now, so my goal then is to like show that this is larger than m, given that I can make the little n sufficiently large. All right. So this, I can take the natural log of this inequality. Natural log's an increasing function everywhere. So it preserves inequalities, like so. But then, of course, that's the inverse function to the exponential, so I get 3n plus 2. Let's look at my natural log m. And then, all right, so that looks like I'm going to need n is greater than or equal to natural log of m minus 2 over 3. So maybe I should make the ceiling function by big N, like natural log of m minus 2 over 3. But then I was like, oh man, the way I defined ceiling was for integers. And so like if this thing was like minus 10, then the ceiling function would give me a negative n. And that's not quite kosher for what we're doing here. So, so what we'll do is just tweak it just a little bit. We'll let n be the positive integer, which is smallest and yet larger than natural log of m minus 2. Haha. So if this is negative, that makes that 1. All right? So let n be greater than 0, and let big N be the smallest positive integer, which has the natural log of m minus 2 less than or equal to n. All right. Observe. Oh, man. I was going to white that out. Sorry. I don't have I'll fix it in a minute. If n is greater than or equal to big N, then the natural log of m minus 2 is less than or equal to big N, which is less than or equal to n. Hence, log m minus 2 over 3 is less than or equal to n. And so the natural log of m is less than or equal to 3n plus 2. And since the exponential is everywhere increasing, I can take the exponential of an inequality and preserve the inequality. By the way, you are free to use the fact that the natural log and the exponential are increasing on their domains in your homework. I'm talking about mission 10 of spring 2025, to be clear. But anyway, so that gives me that m is less than or equal to e to the 3n plus 2, which of course we can reread as if n is bigger than big N, then the e to the 3n plus 2 is greater than or equal to m. Therefore, we've shown that the value of our sequence, namely e to the 3n plus 2, can be made as large as we like by taking n sufficiently far out there. And so therefore, by the definition of divergent limit, we have e to the 3n plus 2 limits to infinity. All right. So, by the way, while we're talking about all this concept of infinity is quite different. Quite different than the concept of infinity that we've been talking about last week with cardinality. Right? Aleph naught is not equal to this infinity. Aleph 1 is not equal to this infinity. These are wholly separate concepts. So this is one of my pet peeves when philosophers start talking about infinity as if it's just one thing, as if it has to be one thing. It doesn't have to be one thing. There are separate concepts of infinity, and Cantor proved that there's in fact a whole string of infinities which are separate and different from one another. So don't believe the philosophers. Anyway, thanks guys. Happy Easter, by the way. Bye.